Hi, welcome to the lecture on EnvAdapt adaptation of animals. Now we will deal on the thermal relations on the endotherms, so how the homeothermy is kept in the mammals and birds. And the homothermic regulation is based on three simple things. You need a thermometer, so a sensor to detect that, okay, what is the temperature. Then you need a reference signal to tell that, okay, what is the normal temperature. And you need a controlling mechanism. So a way to heat the body up or cool it down. And the thermometer is just an ion channel. We have ion channels that are activated in hot temperatures, ion channels that are activated in cold temperatures. And they are evolutionary very old and exist also in the ectotherms. And surprise, surprise, that's why the ectotherms know that, okay, what is the body temperature, so they can have these behavior changes to cool the body or heat it up. And mammals and birds are just using these same things and putting them all together. And it's been done independently, so although mammals and birds are having pretty similar thermoregulation, there are also some differences. And let's first think that, okay, how the thermoregulation is working in normal level and when we have a fever. So there's always some fluctuation in the thermoregulation or the body temperature. So we have a set point, for example, in human, 37 degrees Celsius, but the body temperature is a little bit above it. Then we cool down, then it's below the setting point, etc. So it's fluctuating all the time. And some of this fluctuation is also happening in the daily rhythm. So we have a little bit lower body temperature in the at night time and higher body temperature in the daytime. But then, if we are having a difference in the set point, that causes that, okay, our muscles are shivering and there are differences in the vasoconstriction. So the diameter of our blood veins and arteries are changed, and that causes that, okay, there's either more blood in some part of the body or less blood, and this affects that, okay, then the body temperature can rise. And then it fluctuates again around the setting point. And then, I hope quite soon, we will be able to move the setting point back. And now we are not shivering, but we are sweating to reduce the heat. And also there are some, again, changes in the vasoconstriction. And then we can set the temperature back around the setting point of the thermoregulation. So it's not too complicated. Okay, and this thermoregulation affects on the metabolic rate. So we learned previously that the basal metabolic rate in endothermic animals, we must do it in the thermoneutral zone. For example, in humans, between 25 and 30 degrees Celsius. And if we are having the human in 20 degrees Celsius, the metabolic rate is higher. If we are going in 35 degrees Celsius, it's again higher. So the temperature is below the lower critical temperature or higher the upper critical temperature is the metabolic rate is increased. And this is not a theory, it works pretty well in the animals. So for example, white-tailed ptarmigan, American species, but quite near a relative also in Finland, the thermoneutral zone is between 10 and 40 degrees Celsius. So during the winter time, when it's freezing temperatures, it has higher oxygen consumption. And what is the idea behind this increased metabolic rate. We can easily understand it when forgetting for a short while the sweating and the evaporation. So consider on the dry heat transfer. So the heat is transferred with conduction, convection and radiation. And therefore the body temperature, the difference in body temperature and temperature are affecting on this dry heat transfer. So higher the difference is, then more heat is transferred. And usually, for example, the human body temperature is 37 degrees Celsius, but usually our environment is colder. So the animal is losing heat. So this transfer is positive. And in these cases, we can easily put a metabolic rate in this equation with using a coefficient C. And this equation is called a linear heat transfer equation, but it also have some other names. And the C is thermal conductance, so how readily the heat can be moved by dry heat transfer from the body. And these conductance are always quite tricky factors, so that's why it's easier to turn it on the insulation. So now the equation looks pretty much similar, but now there's instead of C, now there's insulation, and that's under this line. So more insulation you have, the lower metabolic rate you have in spite of the temperature difference. So you have insulation layers like fur. More fur you have, more insulation you have, and then metabolic rate is reduced. But the problem in this equation actually is that in the thermoneutral zone, the metabolic rate is constant. And this is caused because of we are able to change the insulation on the thermoneutral zone. So we can increase the insulation in cold all the way to lower critical temperature, or we can reduce the insulation all the way to upper critical temperature. And the modulation of this insulation counterbalance the difference in this driving force, so the difference between the body temperature and the ambient temperature. And this thermoneutral zone varies among the species. In humans, we don't have much fur, but neither does the mice. So in both cases, the thermoneutral zone is about 5 degrees Celsius. But then in the Eskimo dogs, it's 50 degrees Celsius. So they are much more able to modify the insulation. So what happens in the metabolic rate in the lower critical temperature? So we can assume that, okay, the animal is maximizing the insulation in lower critical temperature. So after that, if the temperature is colder, the metabolic rate is linearly increasing in the cold. And this slope of the line is depends on the conductance, and we can also turn the conductance in the insulation. So in the metabolic rate, it doesn't fall below the basal line at the thermoneutral zone. So now you have in this metabolic rate equation actually two different functions. So if it's below the lower critical temperature, then it's on this line, and then if it's above the lower critical temperature, it's constant. And if we are having two different animals with different insulation layer, the insulation layer is not only affecting that, okay, you need more metabolic rate to be active in cold temperatures. But it also affects that, okay, you can't tolerate so well with your insulation layer on this thermoneutral zone. So it limits the temperatures. So even in higher temperatures, you need to increase your metabolic rate. And these equations above, they are a little bit oversimplification. So if you are making a real science on the metabolic rate and how the temperature is affecting, you should not use these, but they are very easy to understand, and that's why we are using it. But what about then in high temperatures? We are having different kind of ways to evaporate the cooling. We can sweat, we can pant, and then the birds, they have this gular fluttering. So they are moving air in and out in the throat and then evaporating water. But also we have hypothermia. So most birds are rising their body temperature in the hot environment. And the problem over here is that, okay, the insulation is minimal. It's minimized in the upper critical temperature, and there's need for active heat loss, and especially when the ambient temperature is above the body temperature. Then, because if you are having this dry heat transfer, it's transferred inside the body, and the active heat loss require energy. So the metabolic rate is increasing when we are using our muscles to increase the breathing, etc. The evaporation is very good because it reduces the heat more effectively. But still, the cost of the ectothermy are quite high. If we are comparing similar size ectotherm, still the cost of endothermy are quite high. If we are comparing similar size mammal and lizard and test them at the body temperature of the mammal, the basal metabolic rate is about 4 or 10 times higher than the similar size ectothermic standard metabolic rate. And okay, it's 4 times or 10 times higher, it's not so bad. But the problem is that, okay, the environment is usually colder than your body temperature. And these endotherms are increasing the metabolic rate, but the ectotherms are reducing it. And this causes that in the wildlife, the metabolic rate is 10 times or even 20 times higher in the endotherms to compare the similar size ectotherms. Thank you.